Hi. Today is the first of our online lectures in response to the coronavirus and subsequent disease COVID-19. We are doing this on March 13th, 2020. This is a part of our MTH 211, which is our Calculus 2 class. And let's see how this works out. Hopefully this setup that I've got here with the document camera, will work out okay. What I want to do is continue discussing improper integrals a bit and get into some issues of convergence and divergence of improper integrals. This is not going to be a polished presentation or anything like that. It's going to be just as scuffed as the sort of presentations that I give during lecture. It's very much off of the top of my head, so I'm liable to make mistakes. Unfortunately, I don't have the benefit of an audience of clever students who are eager to catch me out when I do make mistakes. But we're just going to have to live with that, okay? So let's talk about this integral here. This integral is, as you can see, an improper integral. Why is it improper? It's improper because we have this infinity up here in the bounds of integration. You might note there is another way in which an integral can fail to be proper. That's when there is what we call a singularity in within the bounds of integration in the integrand. A singularity means a place where the integral sort of blows up to positive infinity or blows down, I guess, to negative infinity. Where you see vertical asymptotes and such in the graph of your function. Here, I think you can verify that we do not have any such singularities. This is a rational function, and the singularities where they do occur is when the denominator is 0. And the denominator is 0 when x is negative 1 and x is equal to negative 1/2, as per this factorization of the denominator. Okay, great. So we don't have any of those singularities what we need to worry about, and that's good. But what we do have to worry about is this infinity here. And that's really pretty easy. But even before that, we have to answer the question of how we're going to find an antiderivative of this integral here. Remember that this is this improper integral we think of as being a limit. It is the limit as b goes to infinity of the integral from 0 to b of 1 over x plus 1, 2x plus 1 dx. And this gives us a hint as to how we should proceed in attacking this problem. The first thing that we should do is figure out what this integral here is. And by the way, this integral is a proper integral. That is to say, it's not improper. This integral has no singularities on this interval from 0 to b, and furthermore, we don't see infinities up here or there in the bounds of integration. So this is a proper integral, which we should, in theory, be able to compute using, of course, our usual tool, which is the fundamental theorem of calculus. Now, what we need to do then is find an antiderivative for this rational function here. And how do we find antiderivatives of rational functions? Well, the tool that we've been using consistently is partial fraction decomposition. Please note, this is a reducible denominator. It's not an irreducible quadratic, right? So we don't need to do the whole complete the square thing. What we need to do is real honest-to-goodness work with partial fraction decomposition. So let's do that. Let's, in other words, suspend our calculus work and do a bit of algebra in order to decompose this rational function into simpler pieces. Okay? So first, we take our rational function. And we are going to write what we call the form of the partial fraction decomposition. Now, typically, the first step of partial fraction decomposition is to factor everything in sight. But that's already been done for us. I've very lovingly done that for you. So what we end up with is a over x plus 2 plus b over 2x plus 1. Each of these are linear factors, so they each get a term of this form in the form of the partial fraction decomposition. A and B here, remember, are constants, which we will now presently determine, but as of right now, their status is just unknown constants. They're just numbers, and we got to figure out what they are. Okay, so how can we do that? First step is to try to make the denominator of this side look the same as the denominator of this side. So we can get that done by multiplying this side by 2x plus 1 upstairs and downstairs, and this side by x plus 2 upstairs and downstairs. If we do that, what we get is a times 2x plus 1 plus b times x plus 2 divided by x plus 2 times 2x plus 1. Okay, and because let's look at what we have. What we have here is now that this rational expression is equal to this rational expression. Yes, but you can see now by design we've made it so that the denominators are exactly the same. And when the denominators are exactly the same, and you have two in a pair of equal rational expressions, it must be the case then that the numerators are equal. So what that means is we are allowed to deduce correctly that 1, which is the numerator here, is equal to the numerator here, which is this mess upstairs in this rational expression. Now I'm going to go ahead and expand out that numerator and get 2ax plus a plus bx plus 2b, and then I'm going to collect like terms. So what I get there is 2a plus b times x plus a. Look, I made a mistake. And in the spirit of not wanting to do these videos a billion times over and over again, see, you would have, if I was doing this in front of a live audience, you would have caught this minutes ago. I somehow made it, instead of x plus 1, which was given in the problem, I, for some reason, wrote x plus 2. These things happen. So what I'm going to do is I'm going to correct myself, fix this, make this a 1. How does that change things? This is a 1, right? Therefore, this is a 1. This is a 1 down here as well. And so therefore, when I go to expand, I have 2ax plus a. That's right. But then I have bx plus not 2b, but rather just b. Let me actually just do this kind of thing. It's a little bit easier to see. Is that clear? Sorry about that. I can't erase this either. This is just a piece of paper with a marker. And now I have a plus b, and that's good. Okay? So, yeah, these are all 1s. Ugh. Irredeemably messed this up. I'm only, 8 minutes into the video. Maybe I should start over. But I can't. Who has time for that? Okay, so we have this here. Now what we do is, because we have an equality of polynomials, we set the coefficients equal to each other. The coefficient of x on this side is 2a plus b, and the coefficient of x on the other side, on this side, is 0, right? There's an invisible 0x that no sane person writes. So we have 0 is equal to 2a plus b as one of our equations. And we also have that the constant term on this side is equal to the constant term on this side. So 1 is equal to a plus b. So what we have here is a system of equations, 2 equations and 2 unknowns. We should expect that because the number of equations, which you can also think of as the number of constraints, is equal to the number of variables, which is the number of sort of degrees of freedom in our system here, you should expect there to be a unique solution to this. Okay, so how do we solve it? Let's take this first equation here, and let's solve for, let's say, b. So we learned that 2a is equal to b. Okay, great. That doesn't actually, I guess it doesn't really take us that much closer to figuring out what the values are, but fortunately we have a second constraint, right, which will fix for us either the value of a or b. Watch. So what I'm going to do is I'm going to take this realization, negative 2a equals b, and shove it into the second equation. And if I do that, what I learn is that 1 is equal to a plus negative 2a, right? And now this is like an 8th grade, maybe even 6th grade problem. You know how to solve this. This means that 1 is equal to a plus negative 2a, which is negative a, so that a is equal to negative 1. Now if a is negative 1 and b is equal to negative 2a, then I guess that means that b is equal to 2. Okay? Is that clear? All right, so I think we've done the algebra now, because what we can do is replace this integrand here by a over x plus 1 plus b over 2x plus 1, where a and b are these values that we found down here, negative 1 and 2. Okay. All right, so let's see what we obtain then. This then, so I'm going to start from back up here. This is equal to the limit as b goes to infinity of the integral from 0 to b of a over x plus 1. Let's see, a was, okay, so negative 1 over x plus 1 plus b, which is 2 over 2x plus 1. I'm not sure why I wrote parentheses there. It's totally unnecessary. I got this here. God, I'm touching my face. Okay, so now we got to find antiderivatives for these pieces. Maybe you remember us talking back a while back. We gave a general formula for integrals like this. We said that the integral of like 1 over ax plus b, this a and b are not the same as the a's and b's we've been using. In fact, we've been kind of overloading the letters a and b, haven't we? Well, 1 over ax plus b is equal to, dx is equal to 1 over a natural log absolute value ax plus b plus an arbitrary additive constant c. Well, if we bring that to bear on this problem here, what we learn is that this is equal to, so the limit stays, the limit as b goes to infinity. What we get is negative natural log of the absolute value of x plus 1. And then on this side, okay, so what's playing the role of a here is this 2, right? And what's playing the role of the b is 1. But so we're going to have a 1 over 2 times the natural log of the absolute value of ax plus b plus c. But then notice that we have this other 2 up here. So that 2 by the constant multiple rule will multiply the integral of 1 over 2x plus 1. And so the 2 there and the 1 over 2 there, they kill each other, right? And so what we're left with is the natural log of the absolute value of 2x plus 1 dx. And oh, I'm sorry, not bx. We've done the integral. But what we're going to do now by the fundamental theorem of calculus is evaluate this from 0 to b. Gosh, I wish I had a whiteboard or a chalkboard or something, but this is the best we'll do, okay? Next play is to evaluate this thing at these various values. Well, we have the limit as b goes to infinity of, so we have negative natural log of the absolute value b plus 1 plus the natural log of the absolute value of 2b plus 1. Okay, and then we have 0 that we can shove in. And we remember, we subtract. So I'm going to do good hygiene here. It's not going to turn out to be all that necessary, but let's just see. We're going to shove 0 in, and what we get is minus negative natural log of the absolute value of, now if I stick 0 here, I get 1. The absolute value of 1 is 1, plus the natural log of the absolute value of 1 again. Yeah, and you can see that doesn't matter what they are. It turns out that the natural log of 1, of course, is 0, but these terms here die. You can think of it like they kill each other, or you can use the fact that the natural log of 1 is 0, and it is. So what we're left with then is the limit as b goes to infinity of negative natural log of b plus 1 plus the natural log of 2b plus 1. And at first glance, that might be hard. Now, maybe some of you are aware of the idea that maybe some of you are aware that as b goes to infinity, the natural log of b also goes to infinity. We talked about this, right? Albeit very slowly does it go to infinity, but it does go to infinity. Okay, so now if we believe this, then what should be true? What should be true about this particular limit? Well, this guy here is going to infinity, okay? Although I guess the minus sign in front makes it go to negative infinity, I should say. And then the second term here, we see also, well, that term is going to positive infinity, isn't it? Okay. So then what does the sum of these two things do? Well, this is actually an example of an indeterminate form. This is an example of that indeterminate form, infinity minus infinity. Maybe you've seen it before, back when you were working a lot with indeterminate forms and L'Hopital's rule. And we can bring that to bear here. And the way that we can do that is by exploiting a rule of logarithms that maybe you are all familiar with. Actually, let me back up just a bit. Before I get to that, let me say, you see these absolute value bars here and there? They sure would be nice if we could get rid of them, right? And we can. And the reason is because since b is going to infinity, right, b plus 1 and 2b plus 1, we can more or less assume are always going to be positive quantities, right? Because as b gets larger and larger, b plus 1 also, and 2b plus 1 for that matter, also get larger and larger. And they are both positive quantities, yeah, in particular. And so this is equal to the limit as b goes to infinity of, and now I'm going to write it in a slightly different order, just so it's not confusing, but I could just do it from here. But what I'm going to do is say, this is natural log of 2b plus 1 minus the natural log of b plus 1, and I've dropped the absolute value bars, and I'm happy about that. Next, I'm going to use rules of logarithms. Do you know the one I'm talking about? The one that says the difference of logs is the log of the quotient. So this is equal to the limit as b goes to infinity of log of 2b plus 1 over b plus 1. Okay. Now, this is a very nice situation to be in because there's I don't know if you call it a deep fact, but a very important fact about continuous functions. One of the things which characterizes continuous functions, like natural log of x when x is positive, one of the things that characterizes continuous functions is that you can swap the order of continuous functions and limits. It's one of the really nice things. So in particular, we can rewrite this limit here as the natural log of the limit of 2b plus 1 over b plus 1, thanks to the continuity of the natural log. That's good. Okay, great. And now the question is, how do we kill this limit here? Well, what we see is that this looks like infinity over infinity, right? And of course, what we do in that situation when we have a limit which has this form, infinity over infinity, is we invoke something called L'Hopital's rule. And what L'Hopital's rule says here, and I'm going to indicate that I'm using that by this dumb thing, L apostrophe H. What it says is that we take the derivative of the top and the derivative of the bottom and we take the limit. So we have upstairs a 2 and downstairs a 1. I'm taking the derivative with respect to b, but of course that's just 2, despite whether or not b is going to infinity, whatever b is doing. 2 over 1 is always 2, and so what we end up with is the natural log of 2, and that is the answer to this integral here. Okay? So what this should mean is that if we were to take the integral from 0 to, let's say, 1 billion of this rational function here, we should get a number which is extremely close to log of 2. And as we start increasing, going from 1 billion to 1 trillion to 1 trillion, 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 we should see that number getting closer and closer to the natural log of 2. Okay? All right. Well, that was all well and good. But let me ask like this. Suppose that we didn't actually care about the exact value of this integral. Suppose that we didn't actually care about the exact value of this integral. I just repeated myself. Suppose instead that what we are super interested in is the answer to the question, does this integral converge or diverge? Now sure, this work that we did, this full page of work, as you can see, it's a lot of work that we ended up doing here. This full page of work really does imply the answer to that question. It tells us that this integral here converges. This integral definitely converges. In fact, we can say a lot more than that. We can say what it converges to. It converges to the natural log of 2. And that's good information, I suppose. But what if all we cared about was convergence or divergence? Would there be a way for us to avoid all of this work in order to determine the answer to that question with one of two answers, converge or diverge? The answer is yes. And the results which allow us to figure out whether or not an integral converges or diverges, those are called convergence tests. So I want to say something about convergence tests for improper integrals. Again, the question that we care about, okay? The question that we care about is, does a given improper integral converge or diverge? That's how you spell the word or. Diverge. Results which shed light on this question are called convergence tests. They're not called divergence tests, I don't know why, but they give an answer to the question, does a integral converge or does it diverge? Yeah? Okay. Well, it is very helpful to have a set of integrals for which you can affirmatively state without any hesitation as to whether or not they converge or diverge. And so first thing I want to talk about is P integrals. So P integrals are a special class of improper integral. They look like this. The integral from 1 to infinity of 1 over x to the p dx. These are P integrals, okay? Where P here is just a number, okay? P is just some number. And I'm not making any assumptions about what number it is. It's just some number. And, well, we've seen a couple P integrals already. Oh, let me back up actually. This definition as written actually is a little bit too restrictive. Let's go ahead and make it less restrictive by, instead of requiring this lower bound to be 1, let's say that the lower bound is a. Okay, and we will require that a is greater than 0. And the reason I want a to be greater than 0 is because I don't want a singularity in the interval of integration here, right? And I can see that for this integrand, x equal to 0 typically will be a singularity for this expression, something like that. Well, for all the p's that matter, right? 0 will be a singularity for this expression here. Okay. Okay. So why am I making that an a there? Well, one of the things that we're going to have to get more and more used to in the future is that the behavior of these kinds of objects, and I'm trying to be a little bit more vague than usual, the behavior of these kinds of objects, and in particular the question of whether they converge or diverge, what it really hinges on is not the is not the specific, let's say, lower bound of the integral. This lower bound doesn't really matter as long as the interval is singularity free. This lower bound doesn't really matter. Okay. What really matters as to the question of convergence or divergence of an improper integral, or later on when we learn about infinite series, what really matters is the behavior around infinity, whatever the hell I mean by that, right? What matters is what the behavior of the function is when, in this case, x is very, very, very large. Okay. In other words, what's happening when x is smaller, when x is like still a finite value, does not really make a difference as to whether or not this integral here converges. If I know that this integral converges when a is equal to 1000, then I know that it converges when a is equal to 5. And conversely, if I know this integral converges when a is 5, I will know that this integral will converge when a is equal to 10,000. Okay? So again, the key thing is that if we're trying to answer the question, does this integral converge or diverge, what's going on with the integral or the function sort of earlier doesn't really matter. What really matters is what's going on in the neighborhood or the vicinity of infinity. That's what really matters quite a bit. Okay? And maybe I can make this very concrete. Because after all, like let's say that we have this integral here. Note that by rules of integration, this is exactly the same as, let's say, the integral from b, let's say, a to b, from a to b of 1 over x to the p, I forgot dx, plus the integral from b to infinity of 1 over x to the p dx. And in thinking about whether this thing converges or this thing here converges or diverges, you can see that because this quantity right here is just some dumb finite number, where issues of convergence don't apply because this is a proper integral of a relatively nice function, but all of our functions are relatively nice. This is a proper integral, and so in particular, it's going to be some finite number. What that means is that this if this thing is blowing up to infinity, then of course the thing that's causing that to happen, we know that these things are equal, is that this thing here is blowing up to infinity, right? And if this is some finite number because it converges, then this thing is going to be that finite number minus this finite number. I hope I'm making myself clear. What matters when it comes to questions of convergence or divergence is the end behavior of, in this case, the integrand. I'm going to write that down because it's important enough. So I'm sort of messing myself up here, but what I want to write is what matters in questions of convergence / divergence is the end behavior of the integrand. Okay? So that's why this is all a long-winded way. I tend to get very long-winded. I'm very, especially self-conscious of it right now because I'm on video. But this is a long-winded way of saying that the value of this a here really doesn't matter for questions of convergence or divergence, particularly with respect to these p-integrals. Okay? All right, so let's answer the question of what's going on with p-integrals. So, yeah, p-integrals. I'm going to rewrite this. P-integrals, we have integral from a to infinity, 1 over x to the p dx. A is greater than 0. Okay. here is the fact. So this thing is, it's either convergent or divergent, and it's convergent if p is greater than 1, and it's divergent otherwise. If p is less than or equal to 1. Okay? So this is the statement. This is the statement. And right now I'm just sort of shoving it down your throat. But I can actually prove this for you. And we will. But before we do that, I just wanted to show you some examples of this that we've seen. So remember, one of the improper integrals that we looked at, in fact, the very first improper integral I believe we looked at. Is this correct? The very first one that we looked at was 1 over x. No, the first one we looked at was 1 over x squared. From 1 to infinity. This is a p integral with p equal to 2, right? You can see that, right? This is a p integral with p equal to 2. And was it convergent or was it divergent? Well, if you look back in your notes, what you'll see is that this thing is convergent. In fact, we computed the exact value of this, and I believe that what we found is that this thing is equal to 1. So sometimes what you might say is that this integral converges to 1. That's something that's sometimes said. Okay. So when p is equal to 2 in particular, okay, when p is equal to 2, this p integral is convergent. And that is totally consistent, of course, with this statement that I'm claiming is the truth. Okay. Well, what about if p is equal to 1? Well, that's another example that we looked at, which is this. What we saw here, remember, this ended up being something like the limit as b went to infinity of something like the natural log of the absolute value of b. You can take a look at your notes if you don't know what I'm talking about. And of course, this is infinity, right? Because the natural log function has a graph that looks something like that. And as b gets bigger and bigger and bigger, natural log of b grows without bound. There is no number which represents an upper bound for that natural log function. Gosh, you know, if I was better skilled, I could pull up things like Desmos on my computer and just show you that that's sort of what is going on. Although it's really hard to demonstrate that it goes to infinity through a graph because, as we sort of discussed, you need really ginormous numbers in order to get even modestly sized values for the natural log. All this natural log talk makes you think of exponentials, which makes me think of the coronavirus. Whoopity-doo. Oh. What am I doing now? So, right, this is divergent. Remember that what we mean by convergent is that the limit that is this, that this improper integral is, converges to some finite number, is equal to some finite number. This limit, this is a limit, and it is a finite number. Okay? Whereas this improper integral, yes, it's a limit of natural log of b, and it doesn't converge to a finite number. It blows up. Okay? That's why we say it's divergent. If this limit also were to fail to exist for some reason, then it would also be divergent. Okay? So these are two examples. These are both p integrals. So both these examples here are p integrals. And they're p integrals with p equal to 2 and 1 respectively. The upper one is p integral 2. Down below is p equal to 1. And we can see the consistency with this result that I'm just sort of shoving down your throat and you're accepting. Well, you don't have to accept it. you don't have to just merely take my word for it. I can actually try to prove it to you, yes? So let's see if I can do that. I mean, the way that okay, yeah. Actually, in peering into the future, I realized the following. It's incredibly important that we already know that this is divergent here, right? So maybe you won't see why yet. You don't understand why yet. But it's important that we know the result holds for p not equal to 1. Because if p is 1, oh, shoot, I'm sorry. I misspoke. We know the result holds for p equal to 1, right? That's what we know. Why do we know that? Because when p is equal to 1, we get this integral right here, which we already know is divergent, and that result is consistent with this line right here, that this p integral is divergent. P is less than or equal to 1, okay? Okay, cool. So assume p is not 1, right? There's just no reason for us to need to deal with that case anymore once we've already taken care of it. So we're going to assume p is not 1. All right, then we can go ahead and try to evaluate this integral in a straightforward way. So we have that the integral from 0 to infinity of 1 over x to the p, of course what that is a limit as b goes to infinity of the integral from, oh, not 0, a. From a to, what am I doing? B, from a to b, of 1 over x to the p. And 1 over x to the p, by the way, is x to the negative p power. Yeah? And the great thing about p not being 1, right, the assumption that we've made here, the great thing about p not equaling 1 is that we can use the power rule on this dumb integral, right? If p was equal to 1, we'd have to deal with this natural log thing. But because we can make this assumption, we're just going to use a straightforward power rule. We don't need, I'm actually integrating right now. So, yeah, damn. So we have x to the negative p plus 1 power divided by negative p plus 1. This gets evaluated from a to b. That's the fundamental theorem of calculus there, right? And then we're going to shove these numbers in. So I get b, and I'm going to write negative p plus 1. I'm going to write that as 1 minus p. I don't know why. Just leave me alone. It just looks better to me. 1 minus p minus what we get by sticking a into this. So if we stick a into this, we get a to the 1 minus p power divided by 1 minus p. Okay? So now what we have is a limit of the difference of two quantities. So that limit can break into two pieces, right? The limit of a difference is the difference of the limits. So this is equal to the limit as b goes to infinity of b to the 1 minus p power over 1 minus p minus the limit as b goes to infinity of a to the 1 minus p over 1 minus p. Okay? Now, if you observe this limit right here, this one is totally trivial because the thing that we're taking the limit of there does not have any b's in it. There's no b's in there. There's not a b to be found in there. Okay? So independent of what b does, a to the 1 minus p over 1 minus p, what that is a to the 1 minus p over 1 minus p. In other words, it's itself, okay? It's just the same way that if you were taking the limit as b goes to infinity of like 3.1, the answer would be 3.1. But what about this guy? This limit here is a bit more interesting, okay? What we have, remember, P is just some number. It's not like it's dependent on B or anything. P is just some number, and it's the exponent for this B. Okay? So if we think about it, well, so let me break it down into cases. So case one is going to be when P is bigger than 1. So if P is bigger than 1, yeah, then 1 minus P, can we all agree, is negative, right? It's less than 0. P is bigger than 1, then 1 minus P is negative. It feels right to me. And so that means that as B gets bigger and bigger and bigger and clicks through these larger and larger numbers, we're raising that B to this negative power. And doesn't that mean that that these quantities are all going to 0 because the exponent is negative, right? This means that the limit as B goes to infinity of B to the 1 minus P. So I'm just looking at this piece right now. This is equal to 0. The second case is that when P is less than 1, 1 minus P then is greater than 0. 1 minus P, in other words, is positive. So this means, let's see, how much time have I? Oh my God, it's 41 minutes already? That's fascinating. Wow. Okay, that's fine. Well, this is some good groundwork. I'm not done. Let me hold off on concluding comments. So we have P less than 1, 1 minus P is positive. This means, okay, so if 1 minus P is positive, then look back here, we're looking at B to the 1 minus P, we have a positive exponent. So like you might imagine like it's 1/2, like the square root of B. Or you might imagine that it's like 5, so like B to the 5th power. In all of those situations, what's going to happen with B to the 1 minus P is that it's going to increase in value as B gets larger and larger and larger. In particular, the limit as B goes to infinity of B to the 1 minus P is equal to infinity. I mean, this is just another way, this is like a fancier, more detailed way of saying that this limit doesn't exist. But this is the behavior of it, is that it blows up to infinity. Yeah? Okay. So then, putting these two facts together, what that means is that this blue quantity, this blue rectangle here, is either 0 or infinity, depending on the nature of P, whether it's bigger than 1 or less than 1. If it's bigger than 1, then this quantity here is equal to A to the 1 minus P over 1 minus P, but with an additional negative sign, right? And if it got that additional negative sign, that gives us, well, I mean, actually, it doesn't really matter a whole lot, but what that tells us is that this thing converges. Maybe I'll be more specific. So we can say it like this. I'm going to break it down into these two cases. So that this thing here is equal to, again, if P is bigger than 1, then this blue rectangle is 0, right? And that's by this argument in case 1 here. So we have, and now what I'm going to do is I'm going to take out a negative sign from here and make it get married to that negative sign. So I get A to the 1 minus P power divided by P minus 1. That's what I get for the value of this limit. And downstairs, what do I have? Well, what I see is this blue box here exploding in value, whereas this is just some dumb finite value. So this blue minus red down here in the second case, where P is bigger than 1, when P is less than 1, exactly the opposite. Geez, I wish I could erase. I need whiteboards. I need chalkboards. This paper thing and ink is for the birds. This thing is infinity in the case where P is less than 1. blue thing explodes. A is just some dumb finite value, so their difference is also infinity. Okay? So that proves the truth of this statement. And this statement here we are going to call the Ptest. I mean, haha, I know. Ptest, but that's what we're going to call it. Okay? And it gives us conditions on when this improper integral here is convergent and when it's divergent. Okay. Well, I think that's enough for today. Let's just review what we talked about, all right? Real quick. I'm going to cap this pen because I don't plan on writing anything more. First thing that we did today was, we did this calculation, right? And this was a calculation of an improper integral. And what we saw is that this improper integral, in fact, converged. And it converged to the log of 2. Cool. Okay. Whatever. But then we asked ourselves, we said, okay, what if we were concerned not with the question of what an improper integral converges to, but rather whether it even converges or diverges, period. The question as to whether it converges or diverges, period, does not necessarily require, this is sort of what I'm asserting. I haven't fully made the case to you yet. But the question of whether an improper integral converges does not fully require us to do this monstrous calculation that we did here. Doesn't. Okay. Instead, what this requires us to do, well, is to apply what's called a convergence test. And we're still in the midst of talking about convergence tests. Okay. But one example of a convergence test would be this thing called the Ptest. Okay. And what the Ptest allows you to do is to determine the convergence or divergence of a particular type of improper integral, namely P integrals. And what we know now is that P integrals are convergent if P is 1 greater than what? If P is greater than 1, and it's divergent if P is less than or equal to 1. And I proved it. In fact, I did it a little bit more than that, right? I even told you to what value I feel confused. One sec. No, this is fine. To what value this P integral converges to when it is convergent. It converges to a to the 1 minus P over P minus 1. But again, it's not the value that we care about. It's rather just whether it converges or diverges. Now, you might be asking yourself, why in the world do we only care about whether or not an integral converges or diverges? What use is that to us? Well, the use of it is something called the integral test that we are going to learn about, but in the context of infinite series. Infinite series are just sums of numbers. Now, you might ask yourself, why do we care about that in calculus class? The reason is because where we're heading is trying to get to a new conception, a new representation of functions. Functions are the primary objects of study in this course. And functions are very complicated, as you probably are well aware. So having new and different representations and perspectives on the concept of function is going to be very, very useful for deepening our understanding of how they work, and in particular for our understanding of calculus issues. Okay, so I see that I've been talking now, oh my God, for about 49 minutes. I really want to stop talking now. I also really want to touch my face. I'm going to stop. I'm definitely not going to do the latter. Definitely not. But I am going to stop the video here. Hey, it's Friday. I don't know when you're watching this exactly. I'm hoping that you're watching at some point this weekend. I'm going to make my next video before Tuesday for class. And I think that my plan will be that perhaps you could watch the video and maybe the TAs. I'm not sure what the TAs want to do exactly. I haven't totally been in touch in a good way yet with them, but maybe they'll be there Tuesday morning to help you out with any questions that you have. I'm in the process right now of writing a document, but because of the craziness the last few days, I haven't gotten it completely done yet. I will get that out to you today, and I'm going to put it on the webpage. Okay, I'm going to put this video on the webpage as well. All right. I know this isn't the best. I don't like it as much either. It's not ideal, but I think it's the best thing moving forward. It's the way that we can ethically run this class. Okay. Love you guys very much. See you next time. Bye.